Okay, so before we go into studying the plane waves reflecting or refracting at a dielectric boundary, we need to sort of do some cursory mathematics to show uh, how this situation is different from our plane wave solutions that we have seen so far, right. So, we will start with right. Before we had the Maxwell's equations and we tried to solve it for a simple plane wave solution, we had the luxury of sort of reorienting our axes, right. And we said that I can, without loss of generality, I can keep reorienting my axis so that my final form for the electric and magnetic fields are convenient, right. But now that there is a dielectric boundary or an interface, right, and I can have electromagnetic beams uh, incident on these dielectric interfaces at any angle possible, right. So, now there is a certain reference direction, right, that is set by the planar surface or the dielectric boundary. So, now we have to look at electromagnetic waves that are arbitrarily oriented to this particular plane, right. So, we no longer have the luxury that I can always orient my axes, right. Even now we can do that, but then the interface or the boundary plane becomes something quite complicated, right. So, what we end up doing is we try to fix the plane, right, the interface as one of the axial planes, right, x y or y z or x z, and we look at electromagnetic waves being oriented to that particular plane. Okay. This is only a choice. So, in this case, what do we say? The general k vector can be written as kx ex ky ey plus kz ez. Okay. So, remember earlier we had oriented our k vector along the propagation direction or the z axis, and so it was just kz ez, right. So, now we can basically have components in all three, right, and we are going to demarcate that with the subscript x, y or z, right. So, if I were to ask you what is the magnitude of k, right, it quite simply will be square root of kx square plus ky square plus kz square, right. All right. So, what does Maxwell's equations tell us, right? So, simply the two divergence equations says that E is perpendicular to k, right, and H is perpendicular to k and E is perpendicular to H, right. So, if I take E, H and k in that order, I basically find that these three vectors are mutually perpendicular, right. So, this is something that all four of the Maxwell's equations in combination, right, establish in terms of relationships, right. It gives us a bit more in terms of relating the magnitude of E and H as well through the wave impedance, but nonetheless pictorially, right, if I were to picture these vectors E, H and k in three dimensional space, remember that whatever plane wave I choose to have it interact with this dielectric boundary should always satisfy this relationship, right. So, no matter how random I orient my k vector, E and H always have to be perpendicular to k and E and H have to be perpendicular to each other, right. And remember that the spatial dependence, which was before just written as e to the j k z z, right, transforms to e to the minus j k x x plus k y y plus k z z. Okay, still a scalar, right, but the spatial dependence now has all three x, y and z, right. So, this is also sometimes written as e to the minus j k dot r, right, where your r vector is simply x e x plus y e y plus z e z, right. Okay. So, I would say that our analysis of plane waves reflecting off of dielectric boundaries is one of very careful bookkeeping, right. So, I highly encourage all students who are watching this video to just follow along, right, and I would say pause or take small breaks, ensure that you also have a pen and paper with you and you are sort of working through this, right. So, I would recommend all students to at least do this once by hand by themselves, right. Okay. A few other things that we can say is the magnitude of E to H at any instant of time is given by the wave impedance eta, right, which is simply square root of the permeability over permittivity for a non-conducting media, right. So, if we just have pure dielectrics, which is what we will consider for the beginning, right. So, for pure dielectrics, the conductivity is 0, and in that case the wave impedance can simply be written in terms of the permeability and the permittivity. Okay. And also the knowledge of K gives you the ability to extract the wavelength in the medium, right. So, this wavelength lambda is essentially a distance in space, right, where the phase difference between two planes of constant phase, right, that are separated by the spatial distance lambda will essentially have a phase difference of 2 pi, right, or you can say basically there is no phase shift, right. So, if I consider planes of constant phase, two of them that are spaced by a distance lambda in the medium, the phase difference between these two planes you can say is 2 pi or 0, right. And we also have a notation for how we represent plane waves, right. So, rather than having to draw something like what I drew a couple of slides back, where I have the k vector here, the E and the H, right. This is sort of like a isometric view, right, or a perspective view, where I am sort of drawing a three-dimensional figure, right. So, I am not too keen on drawing these three-dimensional figures every time. So, we have some very simple ways of representing this on a plane, right. So, I will mostly show a plane wave using this notation, right. So, you will usually see two vectors that are in plane and perpendicular to each other, right, and there will be a third vector that will be basically going into the plane or out of the plane, right. So, in this case I have basically shown a k vector, right, sort of looking at in a northeasterly direction, and then you have an electric field vector orientation, and I have my magnetic vector H coming out of the plane, right, that I indicate with a dot and a circle, right. So, when I draw the collection of these three vectors like this, I am essentially talking about a linearly polarized plane wave, right. So, whenever I show or draw this representation, it should be immediate to you that I am talking about a very specific kind of plane wave. It is linearly polarized. I know the axis of polarization, right. So, the electric field is basically oscillating, right, in the same direction in which I have drawn the electric field vector, right. So, this is a very simple linear polarized electromagnetic plane wave, right, or a transverse electromagnetic wave. So, here is another representation. Okay. So, you have now the magnetic field in plane, right, of my writing board, and we also have K, and those are perpendicular, and the electric field now goes into the plane of the paper with a cross, right. So, basically the difference between the two plane waves that I have drawn is sort of a rotation of 90 degrees, right. Okay. So, now that we have set the basics of what to look for in the diagram and how I am basically breaking down these vector components with respect to a known axis, right, and this axis will be in some way defined by the dielectric boundary. Okay. Okay. So, I have medium 1 on the left side, medium 2 on the right side of the dotted line. Okay. Since these are pure dielectrics, I only have epsilon 1 and mu 1 and epsilon 2 and mu 2, right. So, I have put in brackets two parallel lines, right. This is indicating of something called parallel polarization, right, or transverse magnetic polarization. So, for this we are considering the case okay, where the magnetic field is perpendicular to the plane that we are drawing, right. So, I have considered a cross section which shows the boundary, right, and the magnetic field is perpendicular to this plane. Okay. So, we will have certain nomenclatures, right. So, I am going to call the plane that we are going to study as the xz plane, right. So, the axis that is coming out of the plane is y. Okay. And we define something called the plane of incidence. Okay. Remember, our normal vector is as defined in our boundary conditions, right. It is a unit vector that is going from medium 2 to medium 1, right. So, the vector k and vector n together can define a plane, right. So, the n vector is normal to the interface between medium 1 and medium 2, right. So, we are considering a planar boundary between two media, and this plane has a certain normal direction, right, and a unit vector in this direction is n cap. This in combination with a plane wave whose direction of propagation is k bar, right, can define a plane, right, and this is the plane of incidence, right. So, this is again a definition. So, this is just a way of writing that. So, a linear combination of the vectors n cap and k vector can define all the points in the plane of in the plane in which we are drawing. Okay. Okay. So, we call this parallel polarization. So, you can either say that the electric field is parallel to the plane of incidence, that is the reason for the choice of the word parallel polarization. The two vertical lines is to indicate the word parallel in short, or you can also say that the magnetic field is perpendicular to the plane, so it is transverse magnetic, right. So, what would be the other kind of polarization? It would be the perpendicular polarization, which we will come to next. Okay. In which case the electric field is perpendicular to the plane of incidence, right, and the magnetic field is parallel to the plane of incidence, right. So, we will come to this in our second case, right. What is interesting from the experiment that I showed is that these two cases are different, right. The way that these plane waves interact with the same boundary, right. Nothing about the media has changed, it is just that the orientation of the electric field oscillations has been slightly changed, right, and we notice that there is a difference. So, I think I have laid down a lot of the groundwork that is needed to start some analysis.